So I kindly welcome you to the Hitchhiker's Guide to the Capacitor World. My name is Stefan Menzel, and I would like to introduce you some interesting things about capacitors. I'm working for WE as a product marketing manager now since 7 years. 4 years I was in the field of quality, and since 3 years I'm in the field of capacitors. And I want to take you on the journey through the world of capacitors, and I would like to start with a small agenda. So we will talk about some technical basics on particular capacitor types, and the second stage about the characteristics of film capacitors, aluminum E-caps and MLCCs, and in the third stage about summary and outlook. To directly dive in, I would start with a parallel plate capacitor, an old principle that everybody of you may be aware of. Especially for a manufacturer, there are 3 parameters that are mainly driving the development in case of capacitors. These are the electrodes itself, so the surface area of the electrodes, the dielectric material you bring in between, and the distance you have to the dielectric and in between the electrodes. As you can see, the small formula at the bottom side for the calculation of a parallel plate capacitor. Yeah, it's very simple. So you have the permittivity, the surface area, and the distance. And nowadays, still, these 3 parameters are mainly driving the capacitor development. Why? Because still 90% of the capacitors you can find worldwide are basically made out of this principle. No matter if it's an E-capacitor or if it's a MLCC, for example, they're still basically consisting of a parallel plate capacitor. Some of them are just winded parallel plate capacitors, but still this principle is in charge. So what we have here, where a manufacturer can manipulate the capacitance itself, it's a surface area, it's a dielectric material, and the distance. And so far, these are still the parameters where the development is mostly going on. And especially for the dielectric material, manufacturers are looking what you can do. Because if we talk about permittivity, this factor is mainly driven by the dielectric, or is driven by the dielectric. So the relative permittivity will be defined by the dielectric material used between the electrodes. And as you can see, if you differentiate the materials, they have way different permittivities. So you see, for example, the yellow marked one, the aluminum oxide or the tantalum pentoxide. These ones are very well established ones. The aluminum oxide, so every time if you do an E-cap, you use the oxide material as dielectric. So in this case, you will have a permittivity of 9.3, and in comparison to tantalum, you see if you would go for tantalum and switch, so you directly can increase due to the linearity of the permittivity in the calculation of a parallel plate capacitor. You directly can boost the capacitance if you still stay with same shape of electrodes or distance. And also some newer materials you will find at the bottom side, like ceramic or glass, and at the top of the chart you also can see some foils and films that are used in case of film capacitors. But how to differentiate the capacitor types? The capacitor types you can differentiate at first in 2 categories. So you have on the left-hand side the fixed capacitors that is also mainly driven or driving the capacitor industry, and on the right-hand side you will find the ones with a variable capacitance. The ones with a variable capacitance like rotary capacitors or trimming capacitors. Still existing, sure, because for some applications you need them to adjust the application, but they're not that main factor for nowadays industry, so they are roughly maybe 3% of the market. Also for the fixed capacitors, the mica capacitors, the glass or the feed-through capacitors, they're not that important, they're still existing, but more important are the film capacitors, the ceramic capacitors, the electrolytics and the supercapacitors, because these are the main drivers nowadays in the industry of capacitors. For the film capacitors, you can differentiate between paper film and plastic film. For ceramic capacitors, you mainly have class 1 and class 2. Sorry. In the past, you also could find class 3 and class 4. Class 3 and class 4, they were cancelled in the 90s because they had very big dependencies to DC bias, to aging, and so they were stopped to produce. And nowadays you only find these two categories. For the E-caps, you can separate between aluminum electrolytics, tantalum, and niobium. So what you change is the anode material, and due to this also the oxide as a dielectric. And for the supercaps, you will find electric double layer capacitors, pseudo capacitors, and hybrid capacitors. Sadly, supercapacitor is not the topic for today, but it's a very interesting field. And if you look for fast developments within capacitors, you will see this in the next years for supercapacitors, because they're getting more and more interesting to replace possible batteries. So what is Würth Elektronik doing in case of capacitors? In case of capacitors, we separate in two categories what we provide. So we have non-polarized capacitors, film capacitors, and MLCCs. And for the polarized capacitors, we provide electrolytics. But also this we can separate in two categories. We have the, let's say, old-fashioned construction principle, aluminum electrolytic with wet electrolyte, and aluminum polymer caps with solid polymer in between. Yeah, and we would start with film capacitors first as category, and talking about the details of this kind of product. For the film capacitors, also here you can separate between two categories of film capacitors. So firstly, you can divide them by the structure of electrode. On the left-hand side, you find the old principle how to produce. There, the electrode itself is a metal film. And as a dielectric material between metal films, you will use paper or plastic. So you bring between two metal films, you bring a layer of paper or plastic in between as dielectric. On top again, some layer of paper or plastic. And then you start to wind this, and this is a film capacitor made of this principle. You separate some short abbreviations depending on the paper or plastic type, so like FP or FK. The newer principle on the right hand side is a metallized one. So they show some benefits like self-healing, what I will explain later. And also due to the fact that you work with metallizations, they are slimmer and not such a thick layer of electrode material, because it's not important how thick the layer is, sure, for carrying current, yes, but for the capacitance itself, it's just the surface area that is important and not the thickness. What you do in case of this type on the right hand side, so you metallize a layer of aluminum or zinc or a mixture of it on paper and or on a plastic film. And so you take two pieces of paper metallized or two pieces of plastic metallized on one side and place them over each other, and you can wind this, and so you get your metallized capacitor. In this case, you can separate between MP or MK depending on usage of paper or plastic as dielectric. On the next page, there's a more clearer view of the process, how to manufacture a metallized film capacitor. This is especially a metallized one. It starts first with a big reel, so-called mother roll of plastic. This, for example, could be polypropylene or polyester, but this is a material what each manufacturer is buying in, because you can get it from a BASF or from DuPont or Toray, but it's a raw material that everybody buys, and it's not manufacturing itself. Metallization is something different. The metallization can be done in-house at manufacturer side, and you take this plastic film, let's talk about, for example, polypropylene, do the metallization on polypropylene at a vacuum deposition system, and then you get a mother roll again, but with metallization of zinc or aluminum. You can do this one-sided, or even if you repeat the procedure, you can also do it double-sided. And then in the second step, you see the production goes for film slitting, and by film slitting you define the pitch of the film capacitor. Because, for example, if you would take a roll of 14 millimeters, so this would be later a capacitor with a 15 millimeter pitch. And in the next step, you go for winding. You take two of these slitted rolls and wind them with a small shift to each other, over each other, and so you get a winded coil. If you increase the has a coil, so you have more capacitance. If the coil is smaller, you have less capacitance. And in the next stage, this coil will be taken and you do a so-called flattening in the fourth step. At flattening, you define if you will have more height or more thickness, because you have to keep the volume of the coil, yes, but you can press it in the direction you like before you coat it or you bring it into a box. And that's the reason why you can find the same capacitance values with different height or different thickness, but mainly they have the same volume. The next stage, for the fifth step, you go with this coil into so-called show patch. So there will be applied a contact layer of metal. It's a spray metal deposition, and afterwards you can do directly burn in, so that some bad areas of metal film can be burned off. But I will explain with self-healing later. And one step, seventh step, you see here is a step what was often done in the past. It's not so common nowadays. Impregnation process that you can do, for example, in a silicone oil tank, that you impregnate the dry coils. Because if there's oil, later there can be no water, because it's every time problematic if water can creep into a capacitor coil, especially in case of film capacitors, because if water creeps into such a coil, you get less isolation resistance, so it can be easy that there will happen a shortage and damage to the capacitor. In the next stage, you take the impregnated coil, do the terminal welding. So you weld the pins on the terminal. So on this side where you applied the show pitch, you can weld the pins. And in the next step, this coil will be, or the final product with pins will be coated. So you bring it into a box or lacquer it. And afterwards, the end test will be applied. Due to the high automation of film capacitors, normally 100% of these products are tested. Yeah, and here also in the next foil slide, you can find construction of a film capacitor. So on the bottom side, you see a cross section of the MKP type. So in the table above, you see MKP. As stated before, MK would be metallized on plastic, and the P stands for polypropylene. Then you directly know the construction principle of the capacitor. If a manufacturer is providing MKP, this means they have a metallized plastic film of polypropylene, and here you see a cross-section of a coil where on the left and right side the show pitch was done. As you see, the foils were shifted with a short shift, because otherwise you would interconnect them with each other and do not get a capacitor. And on the show pitch you see also the pin is welded. And on the bottom side, on the right side, you also see how it works. So you raise up some kind of mini capacitors that you interconnect by the show pitch layer on the right and left side with each other, and so you raise up a bigger capacitor system. Yeah, but self-healing, what does self-healing mean in case of film capacitor? Especially self-healing only can happen for metallized film capacitors. Why? Because the metal layer, due to the metallization, it's less than a micrometer, and due to this is so small that it can burn off. And the base films you can buy, like polypropylene or polyester, they are never 100% fine. So there will be some slight issues with thickness maybe, or even some impurities. And this would be defined, issue places. But you can, in the production, you can do a burn off. So if we apply the voltage, that we can burn off these areas, because it will happen like a shortage between the metallization. If you have a weak area in the dielectric, you get a shortage between the metallized layers from layer to layer, and then you will get such a channel like it's drawn here, like a black channel through the dielectric material. But what happens, the metallization on both sides is burning off, and so the area on the plastic film will isolate itself again. One issue you get over time is if you have often such a self-healing, for example, for a X2 capacitor, if you would again and again apply high pulses, this means that the capacitor loses capacitance over time, and this is pretty tricky to define how fast and how much capacitor is losing, because especially this phenomenon can be increased and can be very bad if humidity creeps into a capacitor box, because if the resistance is lowered, this effect can start, but it can happen that it burn off way bigger areas as with a dry coil. Yeah, also with the film capacitors, I would like to introduce the topic of X and Y capacitors. The X capacitor normally is used as protection for the application against the network, or the opposite way around, that you protect the network from the application in this position. And the Y capacitor, normally you connect to housing or earthing, and what you do is limiting the leakage current, and also that you normally have quite low capacitance values, especially in capacitors for medical equipment. It's sometimes also that you left away the Y capacitor due to the fact that limitation need to be there for the leakage current for the patient. Safety classes for X and Y, you can separate them according to the IEC standard. The IEC standard defines the pulse that is allowed to be applied. So there is a pulse of, for example, for the X1 of 4 kV max, or the epsilon 1 or the Y1 for 8 kV. Due to this, if you know for your application which safety class you have to fulfill, for example, X2, this means that each capacitor needs to fulfill this pulse class. And if a capacitor is stated as X2, for example, this directly means it can be used in an X position, and that it is made for this pulse class. There will be also, in case, for example, of MLCCs, you can find a few types where you have a double classification. So, for example, that they have a Y2 and X1, so it's allowed to use them in both positions. So in the Y position, they can be applied 5 kV, when in the X position they are made for 4 kV, so but then it's released for both positions. And in case of X and Y capacitors, what are the certificates you normally find in case of film capacitors? If you're dealing with a product worldwide, so normally you can find the so-called ENEC. The ENEC is a European certificate, so if you want to sell something in Europe, you will need this ENEC, and normally this is given by the VDE. Then you will find a so-called CULOS certificate for the US market, a CQC for China, for the CCC certification, and you also will find, in case of ceramic capacitor, none of these. You only find the TUV or UL to give a release for the global sales. If we go further for the separation between voltage categories, so also for the separation of voltage categories, in case of X capacitors, you will have normally for X capacitors in the past there also existed 250 volt. Mainly they are not existing nowadays. So what you will find nowadays is 275, and also products for 300, 305, 310. And due to the different voltage levels you will find worldwide. So if you do not know where you will sell your product, it's recommended to use an X2 capacitor with more than 300 volt to be safe by the tolerance of the net voltage. If you know that you will just sell it in a defined market, you also can go for lower voltage levels like the 275. And two aspects about the X capacitors. They are necessary for the interference suppression normally, and what you do with them, you use them in parallel for the application safety, and for the case with the serious usage, one recommendation: don't normally use standard X2 capacitors. For these you will find special products with high level humidity resistance, because it's really important that they do not have a big decrease of capacitance over time, to keep the power supply stable over long term. If we go further for the electrolytics, so this will be the second topic for today, the electrolytics. For the electrolytics you can differentiate, as I said, between the electrodes, so let's say the electrode materials. That's the reason why you find aluminum, tantalum and niobium, and also the properties of the electrolyte can be different, so normally they are wet or solid. Also, you can find some so-called hybrid types where you mix solid particles into a wet solution. This is also possible, but as you see, mainly these are the differences in case of E-caps. You all call them E-caps, but you switch the anode material and the electrolyte. For the anode, as you can see on the bottom side, there's a small table. If you switch the dielectric material like aluminum oxide to tantalum to niobium, you can change the relative permittivity quite fast, so you can easily increase the relative permittivity by switching from aluminum, tantalum or niobium, but this will bring some pros and cons with it, so that's the reason why you find still each three of them. And how do you manufacture electrolytic capacitor? I will explain this on the on an aluminum electrolytic radial type THT one. Also in the first stage you will have foil slitting, so there will be again a mother roll, but in this case it's aluminum foil. So for anode and for cathode you will have anode foils. You slit them, and by slitting here you define not the pitch, in this case you define the height, because later on the thickness of the stripe of the aluminum will define the height due to the winding and bringing into a can. In the second stage you take the anode and the cathode foil and weld the pins on the anode and on the cathode foil. It's a so-called stitching procedure where you bring the pedal tabs on the foils. Then the third stage you bring in so-called separator paper. So the paper spacer between two aluminum foils, because this is later on the carrying material for the electrolyte. So in the stage 3 you wind a dry coil of aluminum foil, anode foil paper, cathode foil paper, and wind such a coil. What you see in the fourth step. Then you go for so-called impregnation step. In the fifth step, for the impregnation, you apply electrolyte, so you bring the dry coil into electrolyte bath, so that the paper will be soaked with the electrolyte. Then you go for the assembly, where you take the wet coil and bring it into the case, or into the can, and seal it with a rubber sealant. Then you go for sealing, where you do the beading and bring on the insulating, the shrinking tube on the component. Then we'll have a post-forming procedure to apply the oxide layers, or to establish the oxide layers perfectly inside the product, and afterwards also here, due to the high automation grade, 100% testing. This is a procedure of a standard electrolytic capacitor where you have a wet electrolyte. Also, if you go for aluminum polymer capacitors where you have a solid material, it would be similar from the production process, but it would be different from step 5 to step 6. So, because for step 5 you would not apply a wet electrolyte bath, you would apply a fluid monomer first, and with this fluid monomer you soak the coil, so you soak it with a fluid plastic and not with a wet electrolyte or fluid electrolyte. And afterwards you apply a temperature procedure to form or to polymerize the monomer to a solid polymer material, and this conductive material, the solid polymer, will replace the electrolyte from a standard ECAP to a polymer capacitor. Yeah, and in the construction of an aluminum electrolytic capacitor, also here you can find a cross section on the right side, because this is how it would look like inside aluminum electrolytic capacitor. If you slice it, and on the left hand side you see again that you have the anode foil, the cathode foil as aluminum foil, some separator paper in between, and this will be winded. On the right hand side you see on the anode that there is an oxide layer applied, and this is a real dielectric material. So as stated in the slides before, the dielectric is every time an oxide layer on the anode material in case of electrolytic capacitor. For the cathode foil, this name is not so perfect, because yes, it's on the cathode side, but it is not the cathode itself. It's just for conducting from cathode to pin, because the cathode itself will be the electrolyte. That's also the reason, and now you understand, when you lose electrolyte by drying out over time, that you lose your second plate, so you lose the cathode side. That's the reason why the capacitance decreases, and also the ESR can increase due to the fact that the conductivity to cathode foil or pin gets less good over time. Yeah. Also, what is problematic, if we turn the polarization, so you can say it's a half-conducting material, so oxide layer. So what really happens if you apply the voltage in the correct direction, you can use this product as a capacitor. But it's problematic if you switch the polarization. Why? Electrolysis in the product will start, so the oxide layer would grow. And due to this, also gassing would happen, and this is a case where also traditional aluminum electrolytics can explode, and why you normally can find a vent on top of the product to avoid that the capacitor explodes in undefined direction, so that you have a predefined direction where the gassing can reduce the pressure again. Because if we compare polymer variants with aluminum electrolytic capacitors, we really have to say, you see also on the right side with this vent, normally you have a kind of pre-slicing or pre-damaging of the top of the component to make it afterwards possible to use it as a vent. Aluminum electrolytics nowadays you can go up to 600 volts. They're cheap due to the high amount of used products worldwide. They have a better leakage current behavior in comparison to polymer, and what you can calculate for a formula of thumb. You can normally do a calculation by each 10 degrees you get down by the temperature of product in the application. So if you have, for example, a max temperature of 105 degrees for a product and get 10 degrees down to 95, you can double the expected lifetime of aluminum electrolytics, and that's the rule of Arrhenius. To calculate this for polymer capacitors, we really have to say as a very small ESR values, they have a high allowable ripple current due to this, and also you have less self-heating due to the low ESR. You have no real dry out behavior like aluminum cap due to solid electrolytic material, in this case polymer. They have a higher expected lifetime and load life. They're limited in size. The impregnation process doesn't work for very big coils, so we can just go for cans or cases like 10 multiplied with 12, and maximum also in the market you will find voltages of 200 volt. The load life calculation is also different, so for the load life calculation you separate here to the standard E-caps, and by 20 degrees you can multiply with factor 10. So this means if you get down, for example, for 2000 hour component with 105 degrees, by 20 degrees in the application to 85, so we already would have 20,000 hours of expected lifetime. This is also here shown in the table, how to understand the table. In the table there's stated every such black values per each line or each row. For the aluminum polymer, for example, when you have 125 degrees with 2000 hours printed in fat black, this means this is the value given in the data sheet. So this is a product made for 125 degrees with 2000 hours, so in the second column 2000 hours, and in the third column it would be a 105 degree product with 2000 hours. Following columns for E-caps, again similar, 105 degree 5000 hours product, 105 degree 2000 hours expected lifetime, and the last two columns would be 85 degree products max temperature with 5000 and 2000 hours. And what you can do, you can rate down, if you know the capacitor temperature in your application, by rule of thumb you can estimate the expected lifetime, as you can see here, and even in the comparison you see that polymer is fastly growing in expected lifetime by reducing the temperature. And this is also shown in the chart here. In this chart you can see the blue and the orange curve that is not cutted, and these ones are the polymerics, and the polymer types, as you can see, even the 2000 hour type against the aluminum one with 7000 hours will be very competitive. If you go down to temperatures below 70 degrees, then the polymers really show their big benefits of expected lifetime and are very interesting for quality or long-term stable needed applications. Yeah, also what you should keep in mind when you switch from standard electrolytic E-caps, so all the time I'm talking here about aluminum types, no tantalum, no niobium, to polymer E-caps. So you will have a decrease in permanent applied voltage to 80-90% of the rated voltage. So the standard E-caps max normally you have 70%. The resistant to temperatures will be down to minus 55 degrees. because solid material doesn't change from fluid to solid, because it cannot freeze. For electrolytic it's different, so you do not have the problems with low temperature in case of polymer like you have it with electrolytics, where you also can damage them if they were stored for before application too long at -degrees, and if you run up your application, this can also damage the ECAP if the electrolyte was freezed. What you have to keep in mind, due to the low ESR, you have a higher leakage current, so especially in battery applications you should watch out. And if we go further for some examples of mounting style, also you will find every time the polarization. There are some hints given by the manufacturer for each type of product to find the correct polarization of the product, like radial types, by the shrinking tube, by the length of pins, the SMT chips, the vertical chips where you have it on the base, the angular side of the base, and this let's say half moon, what you mark on the top of the component, or the snap-in types where you also do it with the shrinking tube and the marking on one of the claws. Also, I want to show you some possibilities of pin treatment. So what you normally can do with the pins of a THT product, you can cut them, you can crimp them, you can bend them. This can bring you some benefits, especially if you want to avoid wrong polarization. In the second column in the middle you see one like with a small U in the pin. This is also one of the possibilities when you cut pins to avoid any wrong polarization, or also bending with 90 degrees is something customers like to do if you want to switch the thickness of the cap to the height, so you bring it flat on the PCB and the component is not that high anymore. This is also an option some customers like to go. So just some hints what you can do in case of cutting, crimping or bending. And also what you can find in case of ECAPs, normally each manufacturer will provide tables where you have some basic products, and then it starts that you have some high temperature variant, some long life, so low high temperature. Watch out if you check for a specific product that you follow such things, and that there are often specific series where you can get more specific parameters due to the fact that they're often used more costly raw materials. So they're higher in pricing often, but you get the technical benefits you need. So just as an example, you will also find this for our products or products of competitors. And I would like to go further with the topic of MLCCs. So the third category for today is the multi-layered capacitors. The construction of MLCC, you will have something happening in the market that is already done. There was a switching from quite noble materials like silver or copper or palladium, silver to copper. So that was switching from mostly the noble metal elements to less noble metal elements, because it was just a question of cost. Because nowadays a 100 nano or a 10 nano or 1 nano product, they cost less. The product itself costs less than the packaging. So like a X7R 10 nano 50 volt or 805, normally the product on the packaging costs less than the packaging itself. In this case it's a bit crazy for higher capacitance values, especially microfarad range. It's totally different again, but especially for the buffering capacitors like 1 nano, 10 nano, 100 nano, it's a bit crazy. If we go for the manufacturing process, how a MLCC will be produced, in the first stage you do the so-called powder milling. The powder milling, there will be defined grain size of ceramic material, and here you adjust your ceramic material as a powder. Also you bring in an organic binder into this powder, and to make it printable, and then you do a foil casting, and on such a foil of ceramic you print the inner electrodes. And you do this with many foils, and then you stack these layers of foils, and this could be also a high amount. There can be also a few hundred layers to get the desired product. Afterwards, after stacking, you laminate this, then you do still on the wet plates, you do a cutting. Afterwards, you burn out the binding material, go for sintering of the ceramic, and afterwards do a tumbling to get the connection areas for the terminal connection, to prepare this to the termination dipping, because in the first stage you have to apply a dipping procedure because you cannot directly plate on the ceramic body. So first there will be a wet procedure where often copper, also in past silver was applied. For some products it's still silver, and then it goes for the termination plating, where you can directly plate on the copper layer. Mostly it's nickel and tin. And then also here, again, high automation, so testing of 100% of the components, and then they go for packaging and are ready for shipping. Yeah, what you should separate in case of ceramics, so you have to separate between class 1 and class 2 ceramics. Class 1 ceramics are built with titanium oxides. They have a relative low permittivity. That's the reason why you only get smaller capacitance values. They're very linear in temperature dependency, and they have minimum aging behaviors and very low or even down to non-voltage dependency. This is different for the class 2 ceramics. They're built with barium titanate. They get high relative permittivity. This means the capacitance per volume will be way higher than you can expect, like class 1 ceramics with the NP0 or COG. So with X7 or X5, for example, you get way higher capacitance values on the same size. But you buy this, you get additionally some not linear effects and dependencies, like temperature dependencies that is not linear, aging behavior over time. You have a higher voltage dependency, and also due to the fact that the material is ferroelectric, you can get some piezoelectric effects. So the whole time, if you apply frequency, you have piezoelectric effects. But the issue is bigger if you get frequencies in the hearable area. Then you can also get microphonic noise, and it could be that you have a buzzing on the MLCC. So this is really a problem if you have it after IC, and there are some hearable spikes. It could be problematic that it also will happen in some noise on the MLCC, and it's quite tricky to get this away. Also, one hint for the coding of MLCCs is also given by IEC or EIA, and also you see, for example, here's the NP0. It's a ceramics with 0 temperature coefficient and just 30 ppm tolerance, but it's similar for the COG. It's a similar ceramic, so it's but just by name it's a similar definition. If we go further for the class 2 ceramics, normally the EIA system is more common, but what do you get out of this? For example, with X7R, you directly know the lower temperature limit, the upper temperature limit, and the allowed change over a temperature range for the capacitance. So this is not the delivery tolerance, so this is an additional tolerance that happens when you apply temperature on the component. So over the range of product for X7R, it would be allowed that the capacitor has a capacitance drift of plus minus 15%. It's not a must, but each ceramic that will fulfill this tolerance could be called a X7R capacitor. So, and if we go further for the MLCC, for the dependency against temperature, here just some examples of ceramic materials where you see the NP0 as a black line, straight line. It's really stable against temperature. Where you go for MLCCs of class 2 like X7R, X5 or the Y5V, you see that it's not that stable anymore, but also for X7R, X5R, you see they can have less dependencies than the plus minus 15. It would be allowed, so also here watch out, because from manufacturer this behavior can be slightly different, and just take care if you have big changes of temperature in some critical positions where you need a very precise capacitance value with higher capacitance values. In case of MLCCs, watch out to take this in mind, especially the Y5V. You get a lot of capacitance, but it's not a very stable over temperature. So I think this is even for consumer electronics it's a problem, but especially if you go for industry applications, this is not really the capacitor to go for. For the dependency over time, quite similar picture. The MP0 is stable again, and the class 2 ceramics show aging behavior. This is happening by some changes in the material, where you have some reorientation in the material. This effect could be removed if you bring the temperature over 150 degrees. So you just need to heat up the MLCCs over the Curie temperature, and then you can restore the material orientation. But the problem is you don't do this with the whole application, and due to this, sadly you have to live with such aging behavior. The most critical point about ceramics, or especially MLCCs, is the DC bias behavior. The DC bias behavior happens when you apply DC voltage, so you get a loss in capacitance value. This means what you see here for the NP0, again, you can say NP0, negative, positive, zero, really it's a stable ceramics material. But for the class 2 ceramics, and especially I want to talk about the black one, the X5er, these are just examples, so don't take this for series for everything. So these are just examples, and these need to be measured for each component. So we just want to give you here an example for the X5R. It means that you have, if you apply a 25 volt, and this was a 25 volt type, you would have a loss of 70% capacitance. So this is really critical. So this means if you go to the max rated voltage, you will have a drop of 70% of the capacitance. And if this would be maybe a 10 microfarad capacitor, then you would have just 3 microfarad left if you would apply 25 volt on the 25 volt rated X5R capacitor. Normally also you say you just double the rated voltage in comparison to the voltage you use. It's one possibility that is often used, but also here you see when you just would apply 12.5 volt, still you would have a loss of 30%. So really watch out, especially if you have higher capacitance values, like 100 micro. Often you just find them with lower rated voltages, and so it can be problematic, because if the rated voltage gets lower, then you are more prone to this dependency effect, and it could make sense that you take maybe some smaller capacitance values like 47 or even smaller with higher rated voltage in comparison to one bigger capacitor with a lower rated voltage to get more distance between rated voltage and your applied voltage if you want to have a certain outcome of capacitance. Sure, such a replacement just makes sense if you can offer some space on the PCBs. If the integration density is very, very high, it's a problem that you have really take care of, because you're not able to switch to more than one component. Maybe. Also, something I just want to mention for the impedance. Just take note that the impedance will shift even if you have similar capacitance value, similar raised voltage, similar ceramics. If you switch from 04 to 06, 03, or if you change the rated voltage. So what you need is an impedance curve for each product. Normally you can get this by the manufacturer, so feel free to get in touch with the manufacturer to get information about the real impedance curve, because normally they measure this. Yeah, and just to mention, what are the enemies of each capacitor? So here I don't want to show you the father of the capacitors, I want to show you the enemies. And most of the capacitors have 3 critical points. Humidity or moisture is often something what can be problematic if there will happen any creeping into the box, into housing. Moisture often makes a capacitor not long-term stable. Temperature every time is a problem for capacitors, because most of the capacitors like ECAPs or film capacitors, if you apply higher temperature, they really age faster. And this directly leads to the third step, the time. So time is for most of the capacitors the really tricky point, because they are not made forever. Most of the capacitors show some aging behaviors, or even can fail over time due to decrease in capacitance or changing of parameters. Just a small outlook for the product range where we will go for future. So what are topics that we are looking forward? So one is the DC link capacitors, where we are pushing for new products, and also super capacitors is one important product range where we currently in preparation. So this is an outlook where we will go in future, and where we also will go further with Conrad together. And I also just want to say thank you for your attention, and thanks for taking the time and participate here.